In this problem, a car comes to a bridge during a storm and finds the bridge washed out, and the driver must get to the other side. So he decides he's going to leap this distance, this width, with his car. The side the car is on is 18.9 meters above the river. The other side is only 1.4 meters above the river. If he drives fast enough, he's going to be able to leap and get over to the other side safely. But the river is 67 meters. So we want to know how fast the car should be traveling just as it leaves the cliff in order to clear the river and land safely on the opposite side. So in order to do this, we need to set up some equations. So let's start with the velocity equations. Velocity is a vector, and we can break it down to two components. A horizontal component called Vx. And what is that? Well, that's the initial velocity plus the acceleration, and that's in the x direction, plus the acceleration, the horizontal acceleration, times time. Now in this case, we're going to assume that there's no horizontal acceleration. As soon as he leaves this side of the bridge, he doesn't have any acceleration. In fact, he'll be decelerating, but vertically because of gravity. So this piece is not going to mean anything in this problem. Now, the vertical velocity, well, that's equal to the initial velocity in the y direction plus the acceleration in the y direction times time. However, acceleration in the y direction is actually gravity, and gravity is considered negative because it's pulling down. So, in addition, the initial velocity in the y direction won't be there because his initial velocity is actually all horizontal. So this can go, and then this will be a negative, and we could change this to a g. So our new equations are going to be the velocity in the x direction is v naught, the initial velocity, and the velocity in the y direction is negative gt. So now, we can change these. In order to know what speed he has to go up, we have to say that he's going to actually have to cover this distance of 67 meters horizontally. So we have to actually have distance functions. So these velocity functions, if we integrate them, they become distance functions. So the distance in the x direction will be equal to v naught. I'm going to drop the subscript x and just know that's the initial horizontal velocity. So v naught times t, and the distance, the vertical distance traveled, is going to be negative gt squared over 2, just by integration. Okay, so we got this set up. And we know the distance he has to travel in the x direction is 67 meters. And we also know we want him to travel we want him to travel actually a distance of 18.9 minus 1.4, or he actually has to go down 17.5 meters. If you take the difference between these two distances, 18.9 and 1.4 is 17.5, and I make it negative because he's going down that amount. So that's going to be the distance traveled in the y direction. So we could use these two equations to solve for the initial velocity and the time. So initially, what we can do is take this equation here and solve this for time. So if you solve that for time, you end up with t equal 1.8898 approximately seconds. And then you can plug that into this equation and solve for the initial velocity. And if you do that, because we have the time now, so if you do that, the initial velocity that he has to travel with is 35.5 meters per second. And there's one thing I forgot to tell you. How did I know what g is? Well, g on the planet, we're assuming we're on Earth, is 9.8 meters per second squared. So that will have to be in there to solve this problem. You have to know gravity on the Earth is 9.8 meters per second squared. So that's the initial velocity. He travels at 35.5 meters per second. As he leaves this part of the river, he's going to reach to this side safely. Alright, there's another part to this question, and it says, what is the speed of the car just before it lands safely on the other side? So it comes here horizontally, and it's going to come down here, and we want to know what is the speed. So it's going to have some vertical component to speed and some horizontal, because it left at a certain speed here, and it may have some of that still as it hits this part of the bridge. So what is the speed? Speed is the magnitude of velocity. And if you remember, we just found that the initial velocity has to be, in the x direction, has to be 35.5. And we know the velocity in the y direction, when he's so that's his initial velocity that he's moving at, and that is the velocity equation right here as well. That is the velocity in the x direction, it's initial velocity. And the velocity in the y direction is going to be negative gt, which is negative 9.8. And we know it took 1.8898 seconds to get there, so times 1.8898. So those are the two components of his velocity when he lands here on this other side. And so the magnitude of the velocity he's going to hit at, well, that's equal to the square root of this one squared plus this one, negative 9.8 times 1.8898 squared, and that's equal to approximately 40 meters per second. So, strange thing. He left at 35.5 meters per second in horizontal direction, but he ends up with a magnitude of velocity of 40 meters per second, which is greater than the initial magnitude, because remember his vertical velocity was 0 at that point. So how come he actually increases his magnitude? Well, that's because of the force of gravity pulling down on him. So the magnitude of his velocity increased to 40 meters per second, and that's what he lands with. That's the speed he lands with on this side, just before he hits this side.